Thank you so much for taking the time to come to this talk. Really excited to share with you some of the sonification work we have been doing. My name is Jenn Kotler. I'm a user experience designer at the MAST archive, and I'm here with Clara.
I'm Clara Brasseur. I'm a software engineer at the MAST archive.
And we're both working on a project called Astronify. So I'm going to jump right into some of the description. So what is sonification? Sonification is very similar to visualization. It's about representing data, but instead of representing it visually, we're representing it as sound. So rather than looking, rather than doing your analysis using your eyes, you do it using your ears. And here's an example of a sonified light curve that we have made, and this is of a flare. Okay. So why sonify things? Is visualization not good enough? So there's a bunch of good reasons to do sonification. So the first reason is that ears have the special ability to actually detect changes at a much more detailed and specific level than our eyes do. And a good way of thinking about this is when it comes to animation. So we've all seen animated cartoons, and to make a cartoon, you need 12 frames per second. And usually it's a bit higher, maybe in the 20s. And the eye can detect up to around a little over 100 frames per second. Our ear can detect over 1 million frames per second when it comes to how much detail we can hear. So our ears have a much more detailed level of like just this inherent understanding. And what's really exciting about that for astronomy is that it helps us with something called the cocktail party effect. So people, I'm sure you've all been at a party before or at a busy location, and you're holding a conversation or you're focusing on one particular thing. And there might be a lot of other things going on around you. There's noises, other conversation, at a coffee shop, maybe someone's pouring coffee, clinking glasses, there's all this noise, but you're still able to focus on your conversation. We have this ability of filtering out what we're interested in when hearing, and being able to just ignore the noise. So this is really applicable in astronomy because oftentimes there's a low signal to noise ratio in our data. So with hearing, it is a lot easier to be listening for specific patterns and filter out what's unimportant. And that could be a bit of a challenge visually at times. Another strength of sonification that is a bit lacking in visualization is the exploration of data in multiple dimensions. So these examples on the screen give a really good visualization of what this issue is. So on the left, we have a simple line graph that is showing just 2 dimensions, right? There's 2 different axes, and it's pretty very readable and easy to understand. But what if we want to explore 3 different dimensions? Okay, we can map it onto a false 3-dimensional image. It becomes a little bit less readable, but it's still, you can still get some information about it. But what happens if we want to have 5 or 6 variables or more? Okay, so we're starting to try to map all these visual cues onto this graph, but it's becoming really difficult. We have color, size, we have a few things, but honestly, these graphs become less and less readable the more different dimensions we're trying to shove into that visualization. Sound has an edge on visualization in this way, because sound is inherently multidimensional. Things like pitch, overtones, volume, and then sound is much more easily mapped into 3D with headphones or surround sound. So we can really shove a lot more information and more variables more easily into sonification. And the final reason that we're really excited about sonification, and the reason that we're pursuing this project in the first place is accessibility, because our goal in the MAST archive and just as people, we want what we do to be accessible for everyone. And unfortunately, at this moment in time, astronomy there's a lot of barriers that are preventing people who are blind or visually impaired from entering astronomy as a career. And it really doesn't have to be that way. There's nothing inherent about astronomy that requires vision, especially when it comes to data, like studying data, because no one's looking at stars anyway. We're mostly looking at graphs, right? So the big issue that is really holding back people from entering astronomy who can't see is the tools. So what if we can create a tools and sonifications that allow people to study data without having to look at graphs? And so I'm going to play this video of an undergraduate, a current astronomy undergraduate, Sarah, who is blind, talk about how these tools are impacting her ability to enter the field.
From my perspective, obviously, I'm new to the field relatively, since I'm a second year undergraduate, and I think about, if I had been born 10, 15 years earlier, I think I would have had a really hard time getting into astronomy at all. It would have been, there just wasn't the accessibility technology that I needed. And so every little step, things like this, like really matters to people like me. It really makes things possible for me and people like me that just wouldn't have been possible a couple decades ago.
Okay, so that's the why we're doing pursuing the sonification. And now I'm going to pass this to Clara to talk about how with the software we're developing called Astronify.
All right, so I'm the lead developer on this project, and there's an array of different sonification tools that various people are developing for various different purposes and different types of data that can be sonified. Our project is Astronify, and it is specifically designed for sonifying time series data. And so this is an open source Python code base. The code is on GitHub. The documentation is at astronify.readthedocs.io. It's designed for community-driven development. It's currently out in beta, so if you want to try it out, pip install Astronify. And it's currently open for issues and pull requests. This is definitely a package in its infancy for developers who are interested in actually touching the code and working on it. We welcome contributions, but you don't have to. If you see a bug, we always want bug reports, but also feature requests. This is very much a living, growing piece of code, and we're interested in what features would be most useful for users. And then a lot of the goal, as Jenn said, the driving force behind this was accessibility. And a big part of that is designing this to be integrated into standard archive and standard scientific workflows. So on our end, we plan to add this as a download option in the MAST AstroQuery module. So this is a common way that Python users query and download MAST data, and adding sonification right there with it as just another option means that you don't have to go through a separate route if you need or want sonified data. But that's also why we wrote this as a Python code base to begin with. Python is very popular in astronomy. There are a lot of astronomy visualization and analysis tools written in Python that link together, that work together. And so writing Astronify in Python is meant to also make it easily integrated into any Python-based astronomy workflow using Astropy, using existing tools right there as an option, along with the many visualization tools that already exist. Next slide. So what does it actually look like? So the top code rectangle here, that isn't anything sonification, that is just creating some test data. It takes time series data and it looks for, you give it a table type data structure, and it looks for time and flux columns by default, but you can give it other column names. So if you really wanted to try it out with completely different data, you can, although it's been designed with the idea of time series in mind, and so there's probably some configuration you'd want to play around with. And then it doesn't take that many lines of code to sonify it. So you import this Soni series class, which is the object that handles all of the sonification for time series. You give it your table, and then you can set some configurations. So here I've just set some simple configurations, setting the note spacing to 0.2 seconds. So that's the average time between notes. We do scale it based on the time column, but we don't just use the time column raw, because then you get things like you're sonifying Kepler data and you're doing a whole quarter and you don't actually want to listen to it for a month. You want to listen to it for maybe a couple of minutes. And then each note duration I've set to 0.3 seconds. And there's a whole bunch of other configuration options, the same way that you can zoom in and change your scaling when you're looking at plots or images. You can change those characteristics when you're sonifying. And so then you run the sonify function and then play it, and you'll hear something like this. I couldn't hear that. Can you try it again, Jen?
Okay, yeah, let me try that again. Make sure the volume is up. Oh, it is up. Let me try one more time. Did it come through?
I don't think so. It might just be very quiet. We're going to have a couple of others. What you should have heard, if this worked properly, was a rising tone that was very smooth. So you're hearing the sonification of that line. And then I just want to note that there is a bit of different lag between the audio and the video. So the dotted cursor is, if everything was in the same place and we were in the same room, it would match exactly with the sound you're hearing, but they're a little bit off in this case. Next slide. All right, so this is another simple shape. So this is the top of a triangle. So it's going to sound the same way as the one that we didn't hear before, and then it will also come back down. Okay, I didn't hear that at all. Can you try resharing with audio, Jen?
Yeah, definitely. Were you able to hear the video I shared earlier?
Yes.
Oh, okay. That's super weird. So let me stop sharing. And I mean, I wonder if I should take my headphones out. Maybe I messed it up by putting them on. Okay, so screen share, desktop. Oh, wait.
So did you click the share computer audio?
Yeah, hold on. I'm worried I didn't. Share sound. Okay. Great. Okay, let me mute myself. So
we're on the display for the presenter, not the. Okay.
is this right?
That's right.
Oh, wonderful. Okay, lots of fun. Let's try again.
Perfect. Now we can hear it. So you can hear the very smooth, and there's a peak, and then it comes back down. And trust me, the one that we didn't hear sounded like the first half of that. All right, next slide. All right, so this is the top of a circle, so we'll be able to hear how different it sounds. So you can hear that this one is more smooth at the top, and that the rise slows as it reaches the top of the circle. So you can hear the different shape. Next slide. So here is an example of what it looks like to sonify real light curve data. So again, the top rectangle is just of code is just getting the data. So in this case, I've used the light curve with a K package to create a light curve from TESS FFI data. And so then we will go through the same process. In this case, I'm not going to sonify all of the data, just the first 475 data points, so that we can listen to it in a reasonable period of time. And here I've made the note spacing, so the time between notes, very, very small, 5/1000ths of a second. And the reason I've done that is that in this case, I want to be able to hear the large scale variation in this light curve. So this is a heartbeat star. And if you're looking at the plot, you can see that there is sort of two periods going on. There's small scale periodic movement where it goes up and down a lot. And then on a larger scale, that periodic movement is enveloped and gets wider and narrower. And so that's the motion that I want to be able to hear. So I made the distance between individual notes very small. So go ahead and play that. So now you can really hear that sort of heartbeat womp womp of this star. But if we wanted to look at the smaller periodic signal, we would want to make the note spacing a lot wider so that we could really hear those up and down motions. So now I'm going to pass it back to Jenn to do a game with you all.
Okay, awesome. Well, we've come to the interactive portion of this presentation, and I'm hoping, I think there is a chat window in this Zoom call, although I can't actually see it anymore. So
I can see it, so if
yes,
you need
you can
anything from it.
Great. Okay, so I'm hoping that you'll all participate by writing the answers to the questions I'm going to ask you in the chat. So this is a quick little game show. We're going to test your ears. We're going to play 4 sonifications based on real light curve data from the MAST archive. And after each of the sonifications, I'll ask you, did you hear a stellar flare? And so I want you to write yes or no in the chat, and then we'll reveal the answer. And so we heard a flare earlier. That was a bit zoomed in though. So just a reminder of what a flare sounds like. There's a high, since flares are a rise in the amount of light very quickly, they sound like a very high, sudden high pitched, kind of like a blip. And then it goes back to the original sound. So, oh, here's an example. Perfect. Let me play that for you. Okay, so that is what a flare sounds like. Now let's see if you can recognize if there are or not flares in the next examples. So question 1, does this contain a flare? Yes or no? Okay, what do you think? Write in the chat. Can't tell if anyone's writing it, but I hope you're all engaged and writing what you think.
Overall, the general feeling seems to be yes.
Okay, let's find out. Yep, there was a flare, so I'll play it again. And this time we can watch it on video as well. Okay. So now I'll ask again, does this sonification contain a flare? Okay, what do you think? Was there a flare in there? Write yes or no in the chat.
So we're getting both answers, but I think that this one was harder. But the more people say no than yes. Okay, interesting. So let's find out. There was no flare in that light curve. Okay. So now this one is pretty exciting. Listen closely and tell me, do you think it contains a flare? Yes or no? Okay, what do you think?
Was there a flare?
I think this time everyone said yes, and some people said more than one.
Okay.
In fact, we don't know what this is, do we? Because we have one guess in here of the actual star. Do you remember what star we used? I don't.
Oh, I don't remember what the star was. But we could look that up later if
I
anyone
say
did.
I want to check now.
So yeah, my next question was going to be, did you hear anything different about the last sonification? And as some of you noticed, there was more than one flare. So for the next question, I'm going to play it again, and I'm going to ask you to do a slightly different task. I want you to count how many flares you hear and write it in the chat. And let me tell you, this is a little bit challenging. Some of them, there's a lot of flares in there, and some of them are a little hard to hear. So listen really closely. Okay. What do you think? How many flares did you count? And I'm curious if anyone feels like they would have needed to hear it again, because I guess if a few people request that, we can play it a second time.
So the numbers seem to be mostly between 6 and 9.
Mm.
Probably 7 and 8 are maybe the most. Maybe 6, 7, and 8 are the most common.
Okay. That's a good sign. You're roughly all correct. There were 7 flares. This one is the most difficult to hear. Some of them are a lot larger than others. So here, let me play the video. Okay. Awesome
Actually,
job,
before we
everyone.
move on to the next one, I just remembered where we got this from.
Mm-hmm.
So to whoever suggested it was AD Leo, it's not AD Leo, and it's a little bit of a trick, although I didn't intend it to be a trick. This is data that I've been using for a study on stellar flares in Kepler and Galax, and as part of my research, I've been injecting flares. So not all of these flares are real flares. Some of them are injected flares that I designed to look like real flares, and that's why it flares so often.
The magic of code. Okay. So I hope you all enjoyed that exercise, and if you did enjoy it and you thought that sort of thing was fun, we have a much more in-depth version that we're going to be doing at our demo, which is tomorrow from 4:10 p.m. to 4:40 at the STScI booth Zoom. And I'm really looking for feedback where we want to test this with really experienced scientists who actually study flares normally, or not flares, just light curves in general. And we would really love to get your feedback about how the sonification works. And it should be pretty fun, interactive. So definitely consider coming to that. And also, I just want to encourage you to try Astronify. Try with some of your own data. We have lots of information, examples, some videos and animations up at astronify.readthedocs.io, where you could find out more information about how to do all this stuff. You could join our mailing list if you'd like to hear about any updates and future events. We're doing some outreach things, hopefully in the future as well. So it's a really fun project, and we're excited to keep working on it. And with that, I just want to thank you all for coming again, and ask if anyone has any questions. And if you don't want to ask now, but you want to talk to us later, we will be at the STScI booth if you want to chat about sonification. So you could always Slack us there. So thank you.
All righty, look like the questions are coming in. Oh, Clara, did you want to read them out loud, or?
I can read them. So what else besides light curves is sonification possibly used in astronomy? Do you want to take that one, Jen, or shall I?
Yeah, I mean, you could take it.
I mean, spectra, we would like to work on sonifying spectra. There are some teams doing that. The Afterglow Access team that is at the Geneva Lake Astrophysics and STEAM is working on sonifying images. They have some really gorgeous sonifications of globular clusters. There are different types of data require different techniques. And because we have several missions, namely TESS and Kepler, that just produce tons of light curves, we decided to start with that at MAST. Another application would be just sonifying plots, like plots you would put in papers or on slides. Question, any tests of this on 2D arrays? Would be neat to run this as a line across a FITS file. Yes, and that would be the technique that Afterglow Access is using for images as well. For things like astroseismology, is it possible to set specific frequencies? Oh, yes, like if I understand the question correctly, you can set, so some of the configuration is that you can set what you want the center pitch to be, the median of your data, and you can also set the edges. But also, if you have a really specific use case in mind, we've provided a general sonification function that allows a number of configurations, but you can also change that function. So if there is some really specific algorithm you want to use for astroseismology, you can plug in your own, and if it's very useful, we would encourage you to add it to our code base. How are you deciding what type of sound is produced? This is using straight sine tones. We chose not to model specific instruments and instead just use clean frequencies. One of the things that we would like to do in future is to look at using the overtones to express other dimensions of data. So we started with just very clean sine tones. Why did you modulate the pitch, loudness, and timbre when this was a 1D data set? We did not. I think that there's a couple of things going on, and I think that so the loudness is not modulated, but when you have multiple tones stacking up, it can seem like it's modulated, and we don't account for that. And also lower pitches sometimes can sound quieter. Can I play multiple sounds at the same time, e.g. flux and error? Not yet. That is something that I really want to add. I have an idea for encoding the error in overtones, but I haven't had a chance to implement it. Are there sonification programs for school use not involving Python? Jen, do you want to take this one?
Yes. So we've been talking with a lot of other projects. There's a surprising number of sonification projects that are in the works right now. And actually there is a survey done recently, and really interestingly, a lot of them have been started within the last 2 years. There's just really been an influx of people working on various types of sonification projects. And I know of one that is being worked on by a woman in Australia, but I cannot remember the name of the project off the top of my head, and I'm not sure if it's released or not. Is it Sano Uno? Or is that a different one? But the answer is
Sony Kids or something?
Sony Kids, maybe. But they do exist, and if you want to reach out later, if you're actually very interested in that, we could find out for you and get you some names.